All right, here we go for part two. Example two, the best box problem, classic problem that we actually saw in functions and were able to solve better exactly now in calculus. I'm gonna let you spend some quality time with your textbook and read the example on page 142. If you'd like to see this example done out in full, you can see that in the note, but I want you to learn that from your textbook. And the idea is it's an important skill in university is to use your textbook as a resource to teach yourself. So I'm going to skip that one, go to example three, which I think these ones are the most challenging examples in this whole unit, this whole chapter. The what we'll see, this is a distance problem. Two ships passing in the night. So we got ship A sailing due east at blah 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 blah. How close will the two ships pass on their present course? Well, it's hard to get an idea what's going on here without a diagram. So the first part is to draw some sort of diagram. And this is challenging enough because there's actually two things going on here. There's a velocity and then there's a distance, and it's kind of inappropriate to write both of them on the same diagram. So we're going to try our best to do that, but we're going to take care not to do anything silly. So we have ship A here going due east, and I'm making this a tiny little arrow to show that this is a speed that we're talking about at 5 kilometers per hour. Okay, and due east. And then ship B is 10 kilometers northeast. So northeast over here, ship B is over here. And it's sailing south at 4 kilometers per hour. 4 kilometers per hour. And I'm going to, it looks like they might crash, right? They won't. This one will sort of pass in front because it's moving faster and they're kind of at equal angles. And I'm going to change color here to put on this 10 kilometers. Since this here is 10 kilometers, right? And this is northeast. Northeast means this is straight north, this is east, so this is 45 degrees. And that means this is 45 degrees because B is going straight south. That's an important thing, and we'll talk about that when we get to the analysis. But there's the diagram. And you see how there's two things going on. There's the velocities and the distances, and I have to keep those things straight. All right. So because the 5 and the 10 are different units, I can't draw them to scale, right? So I've got to be careful when I do that. So I'm going to go back and think about what I'm required to find. What am I required to find is how close. How close, how close, how close. Well, what I want to find then is the minimum distance between A and B, right? I want to find the minimum distance. And I'm actually going to call the distance D. And that's, I'm going to go to a different color again here. That's the distance between them. Well, it was 10 at the start. I can see that it's closing, right? So this is kind of like the D here, right? And it's not by equal rates, so this is a tough question. This is a tough question. And so let's get into the analysis. Well, what's a distance formula? A distance formula might be, you might be tempted to sort of, if this one keeps going, and this one keeps going, well, they would meet at a right angle, right? And this distance here, if I call this x and this y, well, that's just Pythagorean theorem, right? I could write this as, the distance is x squared plus y squared, right? Grade 10 distance formula. But now I've got too many variables, right? I can't take the derivative of this because there's an output variable d, which I'd like to, we want d prime, find the minimum distance, but we got this x and this y. Well, all right, let's start thinking about an expression for x. And this is tough. This is our brainstorming here. what would be an expression for x? Well, I'm going to change colors again. If I look in this big triangle here, this is 10, this is 45, right? This whole thing isn't x, but I could get a value for this, right? Because this is just one of our special triangles from grade 11. This is the 45, 1 square root of 2. So if I wanted to get this side over here, well, what is it? Well, it's just going to be similar triangles, right? It's going to be 10 divided, this is just 10 divided by root 2, right? 10 divided by root 2. The one, if I wanted to find this side, let's call it little a. I could say then a over 1 is 10 over 2. Yep, okay. I see that similar triangles. And then I can get an expression for a. Well, a is this terrible thing with a irrational denominator. Let's rationalize the denominator, clean it up a bit. 10 root 2 over root 2 times root 2 is 2. So that's just 5 root 2. And notice that's the same thing as this side. So this is 5 root 2, and this is 5 root 2. So in this diagram, that's 5 root 2, and this is 5 root 2. So this x then, x is just whatever I've traveled subtracted from 5 root 2, subtract whatever I've traveled. Well, I don't know how long I've traveled for, so I'm going to say let t be the time that we've traveled in hours. T is the time in hours. Then I can get an expression for x and y in terms of t, right? Because x is just 5 root 2 subtract how much I've traveled in the time, right? And this is just, if this is my speed and I've been traveling for t hours, a little physics formula, I guess, if you want, that's kind of hidden in here. The speed times the time, the speed times the time, and then that's x. And so what would be the expression for y? Well, it's going to be 5 root 2 minus 4t. So hang on. Now I've got now I've got 4 variables. I've got d as my output, and then x and y and t. Well, no, look what I'm going to do. I can put these expressions in this one. So then I've got d is equal to, watch it, x expression plus y expression. 5 root 2 minus 5t, 5 root 2 minus 4t. And I can take the derivative of this because it's only got one input variable, right? And now I'm ready to take the derivative. So almost, actually, because this is a pretty awful derivative to take because it's a chain rule. I've got that function as the outside function. And I got a chain rule, and I got a chain rule within a chain rule, and it's a mess. So I'm actually going to tidy this up a little bit first. What I'm going to do is expand all that and expand that. Now, I'm actually not going to expand that. I'm going to show you that I've done it. And this ends up being, and I'll show you why in a second, 100 minus 90 root 2t plus 41t squared. Here's the reason why. There's the arithmetic. You can pause and copy if you want, or trust me, which is probably the better idea. So there's that expanded to that. I get that formula, and now I can take the derivative, right? So now I'm going to take d prime of this. Actually, I'm going to spend one more step, why not, and write this as this chain rule, which this is way better than the chain rule and chain rule here. So then d prime subtract, and I don't care what this is, by the way. I'm just gonna, that goes there, and then the derivative of the inside thing is going to end up being the most important part, and I'll show you why. The derivative of that's 0. Derivative of this is just the negative 90 square root of 2, and then plus 81t. Why do I not care what this is? Well, have a look. Because I'm going to set d prime equal to 0. Then I have 0 equals 1 over, because of the negative exponent, I got that to the half times this. Squiggle, squiggle, squiggle. Why do I not care? Because if I'm solving this rational expression, all I would have to do is, as long as this thing is not equal to 0, and I'm going to check that, of course, when I get my solution, make sure it's not equal to 0, I can just cross multiply. Then I end up with the top equal to 0, which is fairly reasonable to solve, isn't it? 90 root t equals not 81, I think it's 82. Did you catch that error? Right? The 2 comes down, it becomes 82. 82t. T is 90 root 2 over 82, which is about 1.55 hours. And then solve back, right? You got to put t equals 1.55 back into this formula, and you should get, after you bing, 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 bing away on your calculator, about 1.1 kilometers. So the ships pass within 1.1 kilometers after 1.55 hours. And I just want to show you that this indeed is the case on Desmos. There was our function. Now remember, Desmos doesn't like independent and dependent variables that aren't anything but x and y. So there's the function, and there's the t is 1.55 and the output is 1.10. So that's all good. Andy, I'm going to pause there for a little drink of water and a break, and I'll come back with the third example in part 3.